Section 1.5 is about exponential models. Exponential models and exponential functions are not polynomial models or polynomial functions. Neither are they power functions or power models. They are something else entirely. Again, you should have done the reading for section 1.5 already. And so we're going to look at a bunch of kind of algebraic examples real quick, and then I'll do one more kind of involved example from this section. I've written here the laws of exponents for your convenience. These are algebraic properties of logarithms that I will expect you to be familiar with. In these, I think I'm going to do numbers 25 through 30 in the textbook here for your reference. So these really just amount to performing the laws of exponents, to simplify an expression or to write it in a different way. The first one, number 25, has us starting with p times 3 raised to the 3x. And we're supposed to show that this equals p times 27 to the x. But the question is, why does it equal p times 27 to the x? So here's the work. If we start with p times 3 to the 3x, and I look at my property number 3 here, I know that when I'm multiplying an exponent together, like 3 times x, I can write it as an exponent raised to an exponent. So I can rewrite this as p times 3 to the 3, all raised to the x. And then, of course, I know that 3 to the 3 is 3 times 3 times 3, which is 9 times 3, or 27. And so this is p times 27 to the x, and we're done. With number 26, again, it's going to be the same kind of thing. I want to show that 8 to the t over 3 is equal to 2 to the t. All right, so how does that work? We're starting with 8 to the t over 3. This t over 3 in the in the exponent, I can think of as 8 times 1/3, 8 raised, to the 1/3 times t. Right? T divided by 3 is 1/3 times t. And now I see in the exponent that I'm multiplying two things together again. So just like in the previous expression, we can consider this product in the exponent as an exponent raised to another exponent. In other words, this is 8 to the 1/3, all raised to the tth power. What you remember from section 1.4 is that the 1/3 power is the same as the cube root function. So in the parentheses, I have the cube root of 8, all raised to the tth power. And what we probably know is that the cube root of 8 is the number that we have to cube to get 8, and that number is 2. And so this does in fact equal 2 to the t. For number 27, we're supposed to show that 500 times 1.025 to the 4t is approximately 500 times 1.1038 to the t. Right, we're supposed to check that somehow. And as you can probably guess by now, really this one doesn't have all that much to it. This 4 times t in the exponent, I'm going to interpret as the exponent 4, all raised to the exponent t. So in other words, if I start with 500 times 1.025 to the 4t, I can write that as 500 times 1.025 to the 4, all raised to the t. And then if you check on your calculator, 1.025 raised to the 4 should be about 1.1038. So that this is 500 times 1.1038, all raised to the t. Number 28 is not all that much different. With number 28, we have 1 over e to the x over 2. E is about 2.718. Okay, this is the natural natural base. Okay, it's a number, but it's one of the most useful bases to use for an exponential function. And so in number 28, we're supposed to show that 1 over e raised to the x over 2 is equal to the quantity 1 over square root of e all raised to the x. And we're supposed to show that that's the case. Here are some steps that we can do, some algebraic steps that we can do to verify this. Starting with 1 over e raised to the x over 2. Again, this x over 2, like a minute ago, in the exponent, I can think about it as e to the 1/2 times x. And then because I'm multiplying in the exponent, I can write it like this. I'm going to leave the 1 in the numerator, and then a product of two exponents is an exponent raised to an exponent. So this is e to the 1/2, all raised to the x power. I know that 1 is equal to 1 to the x, no matter what x is, right? 1 raised to 5 is 1 times 1 times 1 times 1 times 1, so of course it's 1. Right, so in the numerator, I want to think about that 1 as 1 to the x. In the denominator, I still have e to the 1/2 to the x. I'm mentioning this because, excuse me, if I'm dividing and both of the exponents are the same, in the numerator and the denominator, I can write it as a single fraction, all raised to that common exponent. In other words, this is 1 over e to the 1/2, all raised to the x. And now one more step, and this is something, again, that you should have gotten from 1.4, is that the 1/2 power is the same as the square root function. So this is 1 over the square root of e, all raised to the x, and that's what I was supposed to end up with. For number 29, we're starting with 4 raised to the x plus 3, and then we're supposed to end up with 64 times 4 to the x. I can show you how that works. Really all it is property 1, the first law of exponent from the other board there. When you are adding in the exponent, like we are to begin with, 4 raised to the x plus 3, my first law of exponents tells me that this is 4 to the x and then times 4 to the 3. Right? If my base is the same, I should add the exponents together. Since I'm multiplying here, I can change the direction, I can change the order of the two factors. In other words, this is 4 cubed times 4 to the x. And then 4 cubed is 64, and so we're getting 64 times 4 to the x, just like we wanted. There's one more problem that I'm going to do real quick. Again, these are just some algebraic manipulations, giving us some practice using some of the laws of exponents. We'll do number 30, and then we'll move on to hopefully a more interesting example. Number 30 here is to see that 12e to the 0.2t is approximately 12 times 1.2214, it looks like, raised to the tth power. In my exponent, initially, I have 0.2 times t. I have a product, and so I'm going to do the third law of exponents here to write that in a different way. But let me do one step first. I know that 0.2 is 1/5, and so this is 12e to the 1/5 times t. Said a different way, this is 12 times e to the 1/5 raised to the t. If we wanted to, right, most calculators will allow you to compute or approximate e raised to the 1/5 power. If we wanted to, we might note that that's the 5th root of e. And again, on most calculators you can compute 5th roots if you want to. And what it turns out to be approximately is 12 times 1.2214, all raised to the t. take a look at the exercises, and if you still have questions about using the laws of exponents, please let me know. These laws of exponents are extremely useful, and I'll use them throughout the semester. So they are worthwhile. It would be worthwhile for you to remember these. The next example is a common exponential model type of problem concerning growth of a population. In particular, the growth of some bacterial population. Exponential functions have a really important feature that they grow. The rate at which an exponential changes is proportional to its size. This is something that we'll see a little bit later on once we start to do some calculus. But it's a defining property of an exponential, and it's what makes exponentials so useful in real life. Exponential functions come up in compound interest problems in finance. You might have heard of that. They come up in radioactive decay problems in chemistry. They come up in bacterial growth problems. They come up in cooling problems for just temperatures of objects. They're extremely useful functions. Again, like I said, this is a common sort of problem here. We have some bacteria culture starting with 500 bacteria, and we know from the lab maybe that the size of this population doubles every half hour. And then we're supposed to answer some questions. How many bacteria are there after 3 hours, after T hours? How many bacteria are there after 40 minutes? And then the last part we'll do is to graph the population function and estimate how long it takes for the population to reach 100,000. For part A, I want to know how many bacteria there are after 3 hours. 3 hours is equal to 6 half hours. Okay, and I note that because in the statement of the problem, I'm given some information about what happens every half hour, right? So initially, let's say when T is 0, right, the size of the population is 500. I'm going to assume here that I'm introducing this variable T. I'm thinking about it as being time, and I'm going to think about it as time in half hours. Right, so initially when I'm just starting, T is 0, and I have 500 bacteria. When T is 1, so this is a half hour after I started, right, or 30 minutes after I started. What is the size? Well, the problem tells me that the population doubled in size. So now I'm up to 1,000. When T is 2, right, this is what, 2 half hours now, right? So this is after 1 hour. What's the size? Well, it doubled from 1 to 2, and so the size should be 2,000. When T is 3, so that's after 1.5 hours, the size doubled again, and so now it's 4,000. And we keep going, right? When T is 4, that's after 2 hours, the size is 8,000. When T is 5, the size is 16,000. Right, and really we decided that we had to go till T was 6 because 3 hours is 6 half hours. And so lastly, when T is 6, my size is 32,000 bacteria. And that's the answer to question A. Question B says, how many bacteria are there after T hours? And here I'm trying to come up with a formula, a function, a population function. Maybe I can notice a pattern with what I've written here. When T is 0, the size of the population is 500. That's the initial size. When T is 1, the size is 1,000. I can write 1,000 as 500 times 2 to the 1. 2,000. I can write 2,000 as 500 times 4, and I know that 4 is 2 to the 2. And so this is 500 times 2 squared. I want to write it, see, I'm going to write all of these as 500 times 2 to some power, and the fact that I'm getting 2 to some power is due to the fact that the population is doubling every time increment. In other words, so if I keep going, when t is 3, the size is 4,000, which is 500 times 8. And I know that 8 is 2 cubed, so this is 500 times 2 cubed. Likewise with 8,000. 8,000 is 500 times 16. And so that's 500 times 2 to the 4. And so maybe here we can see the pattern, right? When t is 1, I have 500 times 2 to the 1. When t is 2, my population is 500 times 2 to the 2. When t is 3, it's 500 times 2 to the 3. In other words, that exponent, the only part that's changing in each of these lines is the t. And so the answer to B, and if I want to know how many bacteria there are after t hours, I'm going to write it as a function, p of t, which stands for the population size at time t, is what? What's the pattern here? It's 500 times 2 to the t. Okay, and again, this is the population at time t, where t is measured in half hours. This is an exponential function. The base is 2 here. The 500 is a constant multiple. This is just a scaling function. You remember from a previous section that when you multiply a function by 500, that corresponds to a vertical stretch by a factor of 500. All right, we have a few more questions to answer here. I want to know with number C, letter C rather, I'm trying to figure out how many bacteria there are after 40 minutes. 40 minutes, unfortunately, isn't all that nice of a number in this problem, right? Because it's not a whole hour, and it's also not a whole half hour. And so I need to figure out, for part C, 40 minutes is what t value? And that's kind of the question here, right? T equals 1 is 30 minutes, right? Because I know that my t is measured in half hours. T equals 2 is 60 minutes, because it's a whole hour. And so 40 minutes is somewhere between 1 and 2. 40 minutes is equal to 30 minutes plus 10 minutes, obviously. 30 minutes is a t value of 1, and then 10 minutes is just a third, right, of 30 minutes. And so this is 1 plus 1/3. Okay, and so 40 minutes is equal to 3/3 plus 1/3, which is 4/3, as far as t is concerned. All right, so to answer part C then, how many bacteria are there after 40 minutes? What I can do is I can plug 40 minutes, in other words, 4/3, the value of 4/3 for t, I can plug 4/3 into my population function in place of t. In other words, this is p of 4/3, which is 500 times 2 raised to the 4/3. And then you can just compute that on your calculator. I think I did. And I got approximately 1259.92 bacteria. Of course, it doesn't make sense to have some portion, a fraction of a bacteria, and so we would maybe say that there are about 1259 bacteria after 40 minutes. We would round down in that case. And the last part D. I want to graph the population function and then somehow estimate how long it takes for the population to reach 100,000. So in part D, my population function, here it is again, is 500 times 2 to the t. To graph this, we're going to graph it in an xy plane, so to speak, but we'll label the independent variable axis as t, as time, and then the vertical axis is the dependent variable, so that's p. In your book, you saw what the graph of an exponential function looks like. As long as this base, right, 2 here is the base is greater than 1, and as long as that's the case, you get exponential growth as your independent variable increases. And so here, right, is roughly the shape of 2 to the t. And then, like I mentioned a minute ago, when you multiply a function by 500, it just stretches it vertically by a factor of 500. We can indicate that stretch by noting the p-intercept here, right? This p-intercept is the value of the population when t is equal to 0. And of course, p of 0 is the initial size of the population, which we were told initially is 500. Right? So here's a graph of my function. Really, in this problem, I don't care all that much about this portion of it because I'm thinking about time as just moving forward, and so I can kind of ignore that part over here. All right, so there's the graph of the population function, and then I want to estimate the time for the population to reach 100,000. So 100,000, again, this is not to scale at all here, but here's some population value of 100,000. Right? If I were to graph p equals 100,000, the graph would be just a horizontal line, right? Just a constant function. Its graph is a horizontal line at a height of 100,000. Right? So there it is. What I'm looking for is this point of intersection. Okay? You can use your calculator, if you have one, to find this. That's one option. We can also do this algebraically, because at this point of intersection, my exponential function, right, 500 times 2 to the t, and this constant function, 100,000, are equal. And so I could set them equal. 500 times 2 to the t is equal, right, to 100,000. And now I try to, what am I trying to solve for? I'm trying to find the time at which this happens. In other words, I'm trying to solve for t somehow. In a later section, we're going to learn about something called logarithms, and that will allow us to solve this exactly using some algebra. But for now, let's see. If I divide both sides by 500, I get 2 to the t is equal to 100,000 divided by 500, which is 1,000 divided by 5, and so that's 200. And so I want to find the t value, so that 2 to the t is equal to 200. You can plug in some numbers, but you'll never get 200 exactly, and that's really, it's kind of unfortunate, because we're looking for a more exact answer than just a whole number that we can plug in maybe. So at this point I would recommend the calculator, right, using the calculator to estimate that point of intersection. It turns out, again, once we have logarithms, we can do this exactly. It turns out that the t value is approximately 7.64. And then remember that the units of t were half hours, right? And so after about 8 half hours, which is about 4 hours, that's when the population reaches 100,000. If we like, 7.64 half hours is about 3.82 hours. Right, so like I said, it takes about 4 hours for the population, the bacteria size, to reach 100,000.